Okay, so welcome back, everyone. Good afternoon, or whatever it is, wherever you are. This afternoon's first talk will be given by Andrei Chesnikov. He'll be talking about e-assessment of graph enumeration problems in discrete mathematics courses. Okay, I'll stop sharing my screen now. Andrei, you can share yours. Oh, you're muted. You're muted just now.
Okay. I guess you see my screen, and then you also see me, and you hear me.
Yep.
These are the three goals for now. Okay, so I will present certain achievements in the direction that is stated in the title of this talk that we have done during the last semester. So this is more or less work in progress and tried once. So before we, what should I press to get to the next slide? Yeah, like this. Before I start speaking on more technical stuff, I would like to describe the educational setup that that I was facing. So I'm teaching bachelor in mathematics course within bachelor in cybersecurity or programming, approximately 200 students, and they are pretty much newbies and everything when it comes to the university studying. So it's the first year, it's first semester, it's a small course, and it's unfortunately the only mathematics course during their three-year studies. So they don't have very strong prerequisites in mathematics, and they, unfortunately, most of them don't have prior programming knowledge. The course, well, it's not called discrete mathematics, but that's what it essentially is, consists of the following parts. So there is some set theory and elementary logic, some combinatorics, some number theory and related crypto like RSA algorithms. So we have some graph theory and a little bit of linear algebra, but in a very, very limited way. So like solving linear equations and not that, and not much more than that. So when it comes to the graph theoretical part of the course, so many students consider it being relevant, and they tend to show a little bit more interest compared to the other parts of the course. And there are quite some relevant applications, like things on network analysis, or the traveling salesman problem, or some other graph traversing things like find the shortest path, or find the cheapest way to fly from A to B, and so on. So the course has traditionally had some focus on the algorithms like breadth first search, depth first search, some or Dijkstra's and Prim's algorithms, and students like it. Unfortunately, when it comes to the question, why actually do these algorithms do what they are promised to do, then students start having issues, and the proofs are inductive, and induction is something that we sometimes take in the course, but they are still rather new with it. And mathematical induction, if you meet it, if it's your first meeting with it, it's kind of a big story. And when on top comes something that is rather complicated, and that you are trying to prove by use of induction, the story gets double as hard. And part of the problem comes from the school mathematics, which in Norway is represented by the lower part of my slides. So you have an equation, and they use the formula, and then essentially the only non-trivial part is to identify, to kind of color the letters, I would say. So where is B and where you should put the B. And then the next non-trivial part is to make the computations, and so then you're done, more or less. And there never comes an explanation for why this formula is actually true. Well, you can compute and put the numbers back, but not something general. And this is something that we want to break, because we think that this is not essentially the mathematics. So if we speak on a little bit higher, with higher level formulations, so we want students to produce something authentical and find some arguments for what they are doing is correct. And this is essentially a proof. So why do we need a proof? Or what actually is proof, and how can you argument that something is correct if you don't have external authority like a lecturer or the book that you can always refer to and say, yeah, it's correct because of that guy told that it's correct. So we actually want students to start experiencing this very special moment when when you're becoming unsure. You have done something and you don't know whether it's correct or not. And looking a little bit further in their development as programmers, then we want them to practice in constructing algorithms, which means working systematic and being aware of the system that they are following. And unfortunately, we cannot just say, dear students, please start doing this. We have to find some lower level problems that actually involve all these elements. So graph enumeration problems, this is a classical subject. There is a famous book of Harry and Palmer on graphical enumeration, which goes very deep in details and shows some ways further in the abstract algebra. But we take it on a lower level, and a typical example could be, could you please produce and show us all trees on 5 vertices? So just find everything that is a tree and that has just 5 vertices. And then the problem naturally divides into 2 collected things. The first one, which is easy, is to just find some trees. The second thing that is difficult, and it is actually opening for the things I shown on the previous slide, find all the trees. And then when I observed how the students work with these types of problems. So at some points, all of them come to me and ask, yeah, but you know, we found whatever, we found 17 of these graphs, but how do we know that there's actually not number 18 in the picture? And for many, at least this is my own personal opinion on the story, this is for many students, that's the first, in a way, the first point when they see something, they have produced the result, and they are in need of the arguments to show that actually this result is something real. So that's one thing. Another thing, that's this is training on solving this kind of problems, gives a training in pure concept. So you should comprehend what a tree is if you are working on this problem. Which is part of our course curriculum. And this is also a good practice in graph isomorphy, where the students have essentially all the time to answer the question, okay, I have an example and another one, are they the same graph or not? And this is also part of our curriculum, so something that study program wants the students to go through and be familiar with. Yes, and all these problems, they are essentially a part of what in the didactic studies, well, it was George Kinnair who has shown me this, given example type of problems. So essentially, giving examples and construction techniques, and this we should understand as the ABC formula for quadratic equations, is rarely sufficient for most learners, as though many people still consider this being mathematics. But to get a deeper understanding, they need to construct their own examples. And then we are up to the next challenge, which is a teacher challenge. We have to assess all this somehow. So besides our practical issues with being 200 students and usually very few teacher assistants, and many being online, and it seems that this is going to be the new normal, so many just don't want to come offline irrespective of the measures we are taking. So there are too many students, that's one thing. And another thing, this is a demanding story. So if we compare to the problem to quadratic equations, there it's sort of easy. Many TAs are getting quite skilled on seeing the error. But these are some pictures that I just found on Stack Exchange with some graph theory questions. Yeah, okay. So for example, on the left, the 6 non-isomorphic trees are listed below. So, but why on earth are they non-isomorphic? So if you're a student assistant who just works like 2 hours a week or whatever, 6 hours a week with this course, and you're getting shown something like this and not drawn nicely like it's done here, but rather on paper with some kind of unclear edges and so on, this is a big story. The picture on the right is, I would say, it's even worse. It does have, though, some data that was clearly meant to sort of show us that these are these are non-isomorphic. But this is not something you can do on the fly. This is something that needs deep analysis, that needs that really the student conversation partner sort of press the brake and starts thinking. And this is not something we can do in the practical setup that we are having. So just to finish the didactic stuff, so this is essentially something that we want our students to come to at the end. And here are some problem-solving techniques. For example, a few mentioned by Paulia in another famous book, How to Solve It. So if you want to list all graphs on 6 vertices and you consider it being a hard problem, could you please do it with 5, 4, 3, or maybe 2 vertices, and then look how the problem develops. So this is about identifying a parameter, and here it's quite natural. It's either it's number of something, either number of edges, number of nodes, or number of something more interesting. And then we look at how structure develops. So this is a sort of preparation to the inductive proofs that are quite common in graph theory, and this is something that can be also done by quite weak students. So okay, if you cannot do it with 6 trees, maybe with trees on 6 edges, on 6 nodes, sorry, then maybe you can do it with trees on just 2 nodes, and so you see how pattern develops. But this is something like this small conversation. This is something that we keep for this private talks, either during office hours or in the exercise sessions. But the biggest story is done by the computer. So when we are coming to the computer business, we need to we meet the next challenge, and the challenge is that we need to input the graphs. And in computer science, there are 3 representation forms, which is matrix, list, or drawing. And we have tried a few. Actually, we have tried all of them. So the illustration here is actually from an exam that I prepared for 1 year ago, and there we have to use some awkward system called Inspera. So, I mean, there is possible to enter. It's possible to enter matrices, but this has to be done in this kind of in the table form. And I mean, come on, guys, there are 5 nodes, and you have to enter 25 entries, and most of them are zeros. Okay, so I have pre-generated zeros. This is possible, but still, this is quite lots. And if you need to enter several graphs, this gets even worse. And then in the analysis of the matrices, you have to take account of different permutations, and there is some other stuff. So lists, that's another thing, which is sort of okay when people are studying Python programming, and then they have a nice picture on the left, and then they have just to store the nice list of lists on the right. But still, this is getting very long. So if they have to input lists manually, this is a big story. Then we still do have some permutation issues, renumbering of the nodes if we want to assess the graphs. And then this is very much error prone. So what we don't know if we formulate problems in this way and students fail. So do they fail because they don't master the tree concept, or do they fail because they do not master the matrix concept, or the same like a graph theoretical concept, or just this matrix list thingy? And this might be not a big story for like third-year students who've done quite a lot of programming and who can who see night dreams in Python. But for the first year and first semester, this is a big story. And all our experience with the student panels is essentially that many complain that difficult input makes them really hate system. Like multivariate analysis with stack, quite many say that we hate stack because it's so hard to enter these large formulas. So the drawing is easy, is natural, and it's a natural representation for those who start doing it. But then we face this challenge of inputting into some computer system. So our solution uses CodeRunner, which is a quite standard plugin for Moodle, mostly meant for programming. So just students write some code, it's run through unit tests, and then if you pass, then you get some score. But then, surprisingly, there is an input type that allows to draw graphs, and there is also a Python package on the nets, which is called NetworkX, that can do whatsoever with the graphs. So we have installed all this on this Job server that runs the Python code. And then we let students draw, and then we get a Python structure from CodeRunner, and then we send it to NetworkX, and then we can just write something like this to assess whether the student's graph was connected or not. And then I see that I do have still a few minutes, so I think this was the last slide here. So I'm going to do a new share. And then I should find my Firefox window, and then that was the conference. And then I made a small quiz with a few questions that we made in our course. So the first question: draw a complement of complete bipartite graph, where first part has 4 and the second one has 3 nodes. So drawing is very easy. I just click like this, and when I shift click, I make an edge, and then it's done. And then I can do check. And so what students see is this CodeRunner test. There's just one test here. So what we have done, this really looks like cheating, I would say. This is a standard function to create a complete bipartite graph. Then we take a complement, which is also a standard function in the NetworkX, and then we just run this check, which says, okay, are these two isomorphic or not? And then done. And then we should get true, but if in this case we obviously are not getting true. And so students have unlimitedly many attempts to get this true. Next example. This is about finding all non-isomorph trees with 6 nodes. So everything is here. So that was one tree, and then I can draw another tree, and then just make it into a tree, and then I try check. So how does the assessment look like? Well, we check whether the graph is simple. There are no loops, and then we create NetworkX structure for the answer. And this is a little bit ugly, but we are doing it graphically. So essentially we draw ourselves all these graphs and then store it and then get this kind of structure. And so we check whether, again, this forest, then it's not a tree, it's a forest, one forest and another forest, whether they two are the same. So this can be clearly done better. So the students essentially see the answers here, because this is just a list representing the graphs. or all the edges. We can see it like this, while the 42, 45, and so on being the nodes, node names. So this can be hidden, and some extra PRT style assessment can be done. So, for example, we can go through all the components, check whether the number is correct, and if it's not, then we can check whether some single graphs are isomorphic with others. So this is kind of a little bit more work, but it's possible to do within the same within this context. Number 3, something like this. What is here? 5 nodes. Then there should be Euler cycle in all graphs. So everything that has an Euler cycle and 5 nodes. So same type of thinking. We just provide an answer and we check whether it's isomorph or not. Here, I guess it's pretty much the same. Just draw some binary tree that has exactly 24 nodes. And what is important with these kind of problems, that there are quite a few, there could be quite a few different answers that we all will accept as correct. Here, I think this was the 5, so 6. Here it's just draw all non-isomorph graphs that are connected and that have four nodes. This doesn't have 4 nodes, but here my colleague who programmed this, he made some dirty trick. He essentially didn't like the idea of showing the graphs in the code, because this code is being shown to the students. So he made a hash table of the real answer and then of the student answer, and so he compared hashes, expecting that then the hashes will fail, will be different if the two sets are different. Still, I think this is kind of all this is trial and error, but still I think the sort of PRT type of thinking with partial points for partially correct. For example, if there are 6, there should be 6 graphs, but student found 5, then this should get some answers. Some student should get some points for this. And then the last, here we actually use CodeRunner as it was supposed to be. So we have decided to actually teach students using NetworkX and graphs. So there's some code that's kind of tutorial. Do like this and you create a graph, do like this, and then you will have nodes, and do like this, you will have edges. And then they should get, they should program, just make some connected graph with four nodes. So this is essentially, I would say, this is a normal programming exercise as people do in this Python programming courses. Just that we have integrated it into our mathematics course, because I mean students have to be programmers anyway, and then they also get some idea how we check what they have done. That was and maybe the last thing. So surprisingly, all this worked, I would say, because these are complex systems, and then you start installing some third-party packages here and there. And we didn't get a single complaint about from the students that something didn't work or was unclear, and this I consider a big way forward compared to like entering matrices, where everybody meant that this is a complete disaster. And then, well, there was also one complaint from students who meant that there was too much drawing and too limited mathematics. But I think that guy sort of was in a way too smart with mathematics, because the non-trivial part is not drawing. The non-trivial part is actually finding all these graphs. So we cannot, in this way, we cannot assess their thinking completely, but in this way, at least we can automate quite a lot. And I think there were a few speakers in the morning who said that we actually make the very limited and valuable student assistant time we use it differently. We use it for consultations and for work on more non-trivial stuff compared to just looking at different pictures and trying to figure out what's wrong there. So this means that students have done it a few times themselves, and when they really don't understand, then they contact me or assistants. Yes, I think that was pretty much what I wanted to show during this half an hour. Any questions?
Right. Thanks a lot, Andre. I'll give a clap. Yeah, there's the link to posting questions to the Moodle pages in the chat, but also if anyone wants to unmute and ask a question now, that'd be great. Actually, I have a question. I hadn't seen this Moodle quiz where you're drawing your nodes and edges. Is that something that you can demonstrate, like upload to the EAMS site an example, or is that something that needs extra?
No, so I can do it, no problem. We can upload an example. So this is a standard feature in CodeRunner.
Oh,
so
right,
Moodle,
okay.
Moodle has to have a CodeRunner plugin. So I talked to Richard Loeb, who is the author of CodeRunner. So he said that all this drawing was essentially one master project of his programming students. So they didn't think that actually it will be used for other purposes. So what we've been speaking with them now, that this will be just sort of a standard type of input for CodeRunner, because we still have to do the conversion of their structures to network X. And then to really use these questions, you have to have different Python packages. For example, NetworkX installed on your Job server. So this is the server that runs the student code that has Python and everything on there. So it's not, I mean, it's not that straightforward, but it's rather easy if you have good access to your IT support.
Well, hopefully Christian or someone could sort that out. That would be great. But yeah, I think it's a really interesting idea to teach proofs using graph theory is a great, because you can really get into the proofs and things. So that's excellent. Yeah, any questions? Let me refresh there's no questions on the Moodle site.
Okay. Yeah.
Okay. Well, if there's no one else, thanks again very much for your talk. And yeah, it would be great to see an example if you could upload that somehow to there's like a play area, I guess, is on the EAMS site.
Yeah, I would say the one maybe last thing. The good thing is that you can really mix this with Stack and other Moodle types. So this all lives on the same platform and same infrastructure. So it's quite important that it's not being separated into different stuff. But so do a little bit of math, do a little bit of programming, and then combine the two.
Great. Excellent. Okay, thanks a lot. Okay, so our next speaker is Chris Graham, who's there, and George Stagg. I'm not sure if it's a joint talk or if it's just Chris.
That's me.
Yeah, and I think Christian is going to play the video as well. So do you have that ready? Great. Okay.
Hi everyone, Chris Graham here from Newcastle University. In this session I'm going to be talking about assessing programming in numbers. This is work done with my colleagues Christian and others here at Newcastle University. So I'm going to be talking specifically about assessing mathematical programming. And I think we've seen during the first week of the EAMS conference the increasing relevance of programming in mathematics undergraduate curricula has been reflected in a number of talks in the first week of EAMS on assessing programming exercises. And my own view is that there are many parallels between mathematics e-assessment and programming e-assessment in terms of opportunities for automatic marking and feedback, and also the place that e-assessment has amongst a balance of different assessment formats. And we're thinking about sort of procedural exercises versus quality of code in a similar way to we might think about quality of mathematics writing. So this talk is going to be quite similar to a talk that I gave at the Numbers user meeting recently, and apologies to people who are seeing something similar, but I will be also drawing upon some of the discussion that we had in week 1 of the EAMS conference. So I'm going to be talking about the motivation for developing a programming extension to Numbers, about how that extension works and how we're using it in our modules. I want to talk a little bit about backgrounds, so the context of this. So in our maths and physics programs, we have compulsory modules in programming at stages 1 and 2, the first two stages of our students' degree. And we focus on 2 languages, Python and R. So Python goes down the sort of route of numerical methods, and R, probability, computational statistics, and data analysis. And these modules are compulsory, and at later stages students use computer programming in group project modules, or it is embedded in modules at later stages. These modules typically have a structure of a 1-hour lecture and a 2-hour practical each week. And this is important in terms of some of the context I'll talk about later. So the lecture typically covers the theory behind the week's content, goes through some examples, and the practical hands-on in a computer cluster, and students will work through what I call a virtual handout, an electronic handout that has exercises embedded inside it. And this is a really popular format with students. They like being able to sit down and for an hour and see the theory up front. They like seeing the module leader doing live coding and making mistakes and correcting them, seeing that process of programming, and then having the sit down session to work through content in their own time. But it has come with some challenges over the past few years, and most significantly, I guess we have students with very different backgrounds and experiences with programming. So some of our students might have done an A-level or taught themselves a programming language, whereas others are really scared of doing anything on a computer. They don't know how to copy and paste and all sorts of things. So that's a real challenge. And what we found in the in-person practical sessions was that our demonstrators were often dealing with what I call low-level queries about the exercises in the content. How do I start this exercise, or what does this mean? And often we were giving a very polite response, that required little more than signposting the students to maybe some content that was immediately above that told them exactly what they needed to know. And of course, what we wanted was to have much deeper conversations with students about programming. Or we'd see this. So we'd see a competent student working away through the material, and gathered around that student would be one or more other students who are lost. Okay, they're looking, but they're not following along anymore. So students working together, but not in the way that we want students to work together, working in a very non-interactive way. So a further issue was about the timing of feedback. So because our students are working through material at very different speeds, finding the right time for feedback on these exercises is difficult. So my students tell me that they like seeing me working through solutions on big screens in the practical rooms. But if I do that, say 30 minutes into a practical, or for a particular exercise, then the majority of students either haven't got there yet, or they've gone past it and it's no longer relevant. Equally, if I release solutions straight away, then they won't try the exercises properly, and the end of the session or the next week is not much better. So this was a challenge too. And in addition, so that's all about sort of formative practice. Summative assessment programming is difficult. So it's difficult to assess in terms of, particularly the marking. So you see little variation between answers, very difficult to give specific feedback and to detect collusion. It's a very time-consuming process. So we were looking for something to help on the summative assessment side as well. So we went down the route of developing an extension to numbers to accommodate programming assessment. And we saw a number of talks over the last week. So we saw a lovely talk from Debbie Euster on using NB Grader in a linear algebra course. There was mention of Code Runner, which is used at University of Edinburgh, I think. And there was a nice DIY solution by Alistair Wallace on Friday. And Alistair made a good point about wanting a system that he had control over. He could do what he wanted it to do, familiar, I guess would be the right word. And that was certainly one of the motivations for going down the numbers route. Numbers was obviously very familiar to us at Newcastle. But there was more than that. So I was interested in tapping into many of the well-developed features of numbers or maths assessment. Things like, that automatic marking, feedback, randomization, the chance to randomize questions. And some of the more advanced things, scaffolding questions into steps or giving hints, adaptive marking, explore mode, all these things that a lot of time has been put into developing in numbers that could be applied to programming. And there were other reasons too. So numbers is very familiar to our students, of course. They use it for on almost every other module that they take at stages 1 and 2. So the familiarity with our students was a big thing. And there was another thing, which is that what I wanted to do was to mix coding questions with other part types, if you like. So say I have a question where I might want the student to write some code and then interpret that code to give a numeric value or a mathematical expression, and then I might want them to make a plot, say, some data. So I saw the coding questions as being a part of an assessment system that did a lot more rather than a standalone thing. So this went through a number of iterations, and our first approach to marking programming in numbers actually didn't mark student code at all. We used what I call a follow-along approach, where the student is presented with their problem in numbers and then goes away and tackles it in their programming software, and then returns an answer back to numbers. And the idea here was that whatever analysis that the student's doing in their software, if numbers can do the same thing in its own internal language, JME it's called, then we'll be able to mark the student's response. And this is useful, and we still use this for many questions, but it's also a little limited because it doesn't directly mark the student's code. In the second iteration, and this is the one that I used a lot over the past year, we did mark code. So we gave students an answer box to enter code into, and that code was sent off to a server running R or Python, along with some unit tests to test on the code, and the server would send back responses to numbers, which in turn would use those responses to apply marking and feedback. And that was very, very usable, but it relies on a server to run the code. So that's not ideal. The server might fall down, but also it's fixed in Newcastle, very difficult to share. In the latest version released this year, we've used WebAssembly compiled Python and R to run code entirely inside a web browser. So we're not relying on a server, and therefore we can share this with others. It's also very numbers-esque, if you like, thing to do, because the rest of numbers runs entirely in a browser. And so that's what the latest version of the extension looks like. And I want to show you an example, very simple example, first of all. So this is about as simple as it gets. So here I'm asked to set a variable x to the first item in a list. and that's marked in the browser and some marking and feedback applied. So the interface will be very familiar to students who've used numbers before, and any of you who've used numbers before. It has a prompt. It can have optional steps. It's got buttons to regenerate if this was randomized, to reveal a solution. And I'm also tapping in here to some of the features. So the alternative answers feature in numbers. So the most likely, I think, mistake students would make here is to forget that Python indexing starts from 0, and I've caught that specific error here. It has validation tests, so if I forget to set X, it tells me that I've not defined X. So that's a very straightforward example, and here behind the scenes, what we're using here is in numbers we call custom part type, and it's the code part type, and if you numbers user, you can go ahead and look that up and give it a go. And again, the interface is quite familiar to a question author, so it has a prompt like any other part, and then some settings, some of which are common with other parts, and some specific to this part type, so the language, the correct answer, placeholder to put some text in before the student's response, some code that can run before or after the student's answer, and some tests, marking tests and validation tests. And there's just one of each for this simple example. I wanted to show you something a little bit more extensive. So this is a question on creating an array or matrix. So the purpose of this assessment was really to become familiar with a particular function which constructs matrices based on values in diagonals. And the nice thing here, so I've added in here randomization. So if I randomize there, I see a similar question, and again, and so on. So if this was a summative assessment question, then every student could receive a similar but different question. If it was a practice question, then I've got available, the show steps feature to give some hints to the student. I'm going to have a go at this. So this function takes 3 arguments. The first is the values on the diagonals. The third one being a range, a list of sequence of numbers. The second is the index of the diagonals, so offset to the main diagonal. I'm not too worried if I get this wrong because I want to show you that anyway. And then the third is the shape of the matrix, so I'll give that a shot. And I get some feedback on my code. We'll find out if I got this right. I didn't. Yeah, okay, I wanted to show you that in a moment. I didn't convert it to a matrix array. There we go. And the nice thing about this question is that there's not just one test. There's not one test checking all of these, just checking that this matrix is the same as the expected one. It's checking, the values along the diagonals. So you can see a number of tests that have been passed. And that means that if I make a simple mistake, like I put a wrong value in there, then I still get a lot of the marks because it's just it's checking and seeing that all of the other diagonals are correct. So it's more sophisticated in that sense. And we already saw there that if I do another common error, which is to forget to convert what's called a sparse matrix into an array, then it tells me what I've got wrong and how to correct it. So that's a validation test that I've added. We talked a bit about about making sure that feedback isn't confusing to students, and I've got a lot of control about when this validation test appears, which helps a lot here to make sure that that's not a confusing message. I can reveal a full set of answers, so full solution, talk the students through it, and just like a maths assessment question, this randomization is specific to the example that I've given, is specific to the randomized matrix. So that's quite nice as well. I'm going to show you another example. So one of the conversations we had last week was about ensuring familiarity with an assessment system. And this is a sort of different type of question. So it's the same thing with marking code, but here I've used the placeholder to input some code, and I'm asking the student to debug it. And the point of this assessment question is to get the student to think about how I would mark a question like this, where I've asked the student to create a function and take in some values and return something back. And this is a common error, so I'm trying to talk to with students about common errors that I see, where actually the function is printing a value, it's not returning it. And I talk through that in the steps feature here about, if they run that bit of code after their function, then what do they see? And hopefully, as they work through here, they can put 2 and 2 together and see that they're not assigning a value to a variable there. And so they can fix it, and submit and get a nice tick there. So I use this quite a lot actually in my exercises, sort of bug fixing things. Okay, so back to my slides. So we talked a bit last week about notes in questions versus questions in notes. And so I go down the route of putting questions embedded inside my my notes, my virtual handouts, as I call them. So these this works quite well. I think it's not quite perfect, but it's certainly very good in terms of how students feel about it. Good feedback about this format. And the new experience is that, well, firstly, during COVID, these modules ran very successfully without any practicals, without any student demonstrators. And so students were able to self-learn, diagnose their issues and work through the material. And since returning to campus, we have seen less of those low-level queries, and we are able to have some of those deeper conversations, which is great to see. In terms of assessment, so I have these embedded exercises. On top of that, I provide what I call test yourself question sets each week, which are a mix of sort of warm-up questions, these sort of debugging questions perhaps, and multiple choice, some code marking questions, and some stretch questions that go a bit beyond, for students who are who've maybe done programming before and are keeping up well with the course material. For summative assessment, I use a hybrid format. So about 60% of my modules used auto-marked questions, like the ones we've shown here. But actually, for a lot of these summative assessments, I'm asking the student to manually submit code or their results, their plots perhaps, for manual marking. And Ben Mestel, in his talk on the Open University on Friday, talked about freeing up staff time. And I see this in a very similar way. We have a finite resource for marking, either in terms of our workload or just time we're willing to mark, or postgraduate marking time. And what this allows is focusing that manual marking where it's most effective. And I was really pleased to see in the student feedback comments like this that feedback from assignments was detailed and personal to us. And if that student saw how little time I spent marking their work, I think they would be surprised. But by using these sort of individual tests on their code to give very specific feedback, and then having the time to focus, and spend more time marking the bits that they submit, I think works very well. Okay, so I am very, very briefly going to show you just a couple of examples. I'll just show them and talk about them. So this is the numbers explore mode. I've pre-prepared a solution here to save a bit of time for questions. And the idea here is that rather than ask them a long question here about creating a rectangle object in Python, it builds it up over steps. So I do the initial setup of a rectangle in Python. I move on to the next step, and numbers uses the adaptive marking to put my solution to first part in the code box there, and then I can add to that with more stuff. So that's quite a nice way to not overwhelm the student with a long question, but give them give them it in little chunks and let them build up their solution. And one that's very experimental. So I don't think I'd use this for summative assessment, but I can see perhaps using it for these sort of handout exercises. So in Python, you can actually mark the properties of a plot. So I can check that this really is a plot of that function over a certain number of values. Okay, would love to talk about that more, but I should finish and leave time for questions. So what's next? So next academic year will be our first full run through modules using this new version of the extension. And I expect there'll be some development, things arising as we move through converting questions for that new academic year. I'm foreseeing us using this more in our R teaching. Next year, I've talked a lot about Python, but all these things also work in R. And, as we go through that new iteration, I expect that we'll develop more public questions. Okay, so if you want to find out more, these slides I think will appear online, and you can check out these links to blog posts and things about the extension. And a big thank you to my colleagues in Newcastle here. Okay, so I'll take some questions. Thank you.
Right. Thanks a lot. Let's give a little applause. Nice one. Yeah, so if anyone has any questions, feel free to turn your mic on and ask, or post in the Moodle forum that's linked in the chat. I have a question actually, which is just so I understand how this works. Code Runner, as I understand it, is kind of relies on Moodle and it runs on the Moodle server. So this is something you're saying runs in the browser. I don't really understand how that works. So are you leveraging some existing technology, it sounds like? Because how does it, I don't understand how like packages and installing packages work. It's very confusing.
We're utilizing some very new developments, and really, so that the R side in particular, this was brand new, being able to run R in a browser. So existing WebAssembly, I might draw Christian to fill in the technical details here. Basically allows you to compile Python such that you can give a Python command in the browser and run it. So there's no server involved. It's not being sent off anywhere. So Pyodide is I think there's an existing package that we're utilizing, and then WebR, which is something my colleague George Stack developed. So yeah, it really is just using the web browser. And there is so on the Pyodide side, there's support for, I think, anything that's built into Python, and then certain other packages as well. So NumPy, SciPy are supported, and I think a number of others. Not unlimited support, I think, for packages. I don't know if Christian wants to add anything.
Yeah, it's just any pure Python package, it can just install as it is because it's real Python, but packages with native code like NumPy, which has some Fortran in the middle of it, has to be compiled specifically. There's a list on the Pyodide website of what they've done.
Great. Well, it sounds like a great development anyway, and really useful for learning. So it'll be good to hopefully report back next year how it went, I guess. Were there any other questions? Oh, there is one in the Moodle page. One tends to see people use Jupyter Colabs a lot to teach code, and it's often people's first go-to. Does the Numbus approach sit alongside that in your approach, or replace it as a preferable alternative?
Yeah, so certainly replaces any sort of assessment aspect of those approaches. So So all of our assessments run through our, numbers plugin to our VLE and that like, and in the actual teaching, these exercises are embedded directly in the notes. Those notes, we have software that generates those actually as Jupyter notebooks or as HTML pages, but either way, they either embed a numbers exercise or link off to a numbers exercise. But we're very much on the assessment side. We're sticking with the same sort of infrastructure around assessment that we use for other modules, so students access them in the same ways. Yeah.
Okay, great. And yeah, Andre, you got your hand up?
Yes, I have a question on this integrated course design. So these notes and exercises all together, like, do you consider it being a really fruitful approach? What are students saying? What are colleagues saying? Is it easy to maintain? Like, some reflections on this?
Yeah, I mean, the feedback's really positive from students, especially when compared to what they tend to see in other modules, which is static PDF files and then their assessment questions, halfway across the VLE. So I think lots of comments about, it being kept together, and they like that sort of integrated approach. The software we're using is specific to Newcastle, basically converting Markdown or LaTeX to web-based notes. There are a number of, I think there was some talk about this last week. There's a number of very similar systems, but I'm a big fan of, having exercises, right next to the course material, rather than sending students off somewhere else to go and find them. Really hit them when it's relevant. Yeah. The tool we use is called Chiron, and it's open source. Christian's just popped a link in the chat there. Yeah.
Great, thanks a lot. We have time for another question. There's someone's hand up, VP, not sure the name.
So that's me, Vesna.
Oh yeah, Vesna. Yeah.
Sorry, yeah, I is missing. So I have completely different question. Being exams officer, how do you involve your external examiners in e-assessment when it's part of a summative assessment?
Okay, so all right. In terms of quality control before the exams are released, or in terms of checking?
Yeah, how they, so usually we kind of send them all our exams, they look through it, make their comments, and so now, I mean, I'm asking because I'm exams officer and I don't know exactly how to,
Yeah, so we do one of two things. So we either send a printed copy of the exam. So Numbers has a called the printable worksheet theme, where you can generate a static PDF effectively with the solutions, with and without the solutions. So either that, or give access to the Numbers editor, to the relevant content. And then on the other side of it, if they need to see transcripts, then again, similar options, either printing transcripts, something we were just talking about today, actually, or giving access to the VLE so that you can get it. Yeah.
Okay, thank you.
Great. Okay, thanks very much. That's it, unless I've missed any other questions. So I guess that's it for today, and we'll see you tomorrow for more talks at 9 a.m. Yeah, okay, well, thanks to all the speakers and everything like that. Okay, see everyone later. All right, bye.